Okay. All right, before this, a couple of announcements. We pushed out the homework 5 due date by 2 days. So hopefully this will give you some time. And looks like this is running out of battery, so I may need to switch to my computer. And get started early on Lab 5. It's due April 6th. So you don't have a whole lot of time. Okay? There are a couple of upcoming events that I encourage you all to attend that are related to the topic of this course. There are some computer architecture seminars that are coming up, and one of them is specifically related to memory, which is next week, April 3rd. And there is a cloud workshop that's on April 4th. So hopefully it should be fun to you. But seminars, there are several seminars that are relevant to many topics covered in 447. So if you want to learn more about what's going on in computer architecture today, you can click this link and you can see the past and upcoming seminars here. They're usually held either in this room or Hammerschlag Hall D-level conference room D210. So far we've had topics on caching and DRAM. And if I click on this, it'll probably take us to a place where you can see the seminars. So you can see some of the topics here. This is not updated, but there's a seminar on April 1st by John Shen, on April 3rd by Rajiv Balasubramanian that I'll talk about. But feel free to attend these seminars. Actually, most of these were apparently in Hammerschlag Hall. Okay, and you can actually subscribe to receive computer architecture-related event announcements over here, if this is your passion, if you will, or if you would like to learn more about it. That information is provided over here in this website. Okay, and Calcium stands for Computer Architecture Lab at Carnegie Mellon, in case you wondered. Okay, there's one particular seminar that I would like you to attend, which is basically related to what we are going to be discussing today and in the next lecture, or in the next couple of lectures. This is going to be on DRAM, and April 3rd, Thursday, 4 p.m. in this room. I think it's at 4 p.m. It's not over there, so I cannot confirm. But Professor Balasubramanian from University of Utah has been doing, his group has been doing interesting work on emerging memory technologies and DRAM technology. So I definitely encourage you to attend. The title is Memory Architectures for Emerging Technologies and Workloads. And you can read the abstract over here. Basically, he'll talk about some research that they've been doing on DRAM parameter variation, how to exploit that. Near data processing, which we will briefly talk about in a later lecture or guest lecture soon, and memory security. So if these are interesting to you, I'd encourage you to attend. Plus, I believe there are free cookies in these seminars. Is that true? Usually. So if you're lucky, you'll get free cookies. Okay. There's also a cloud workshop all day on April 4th, and you need to register to attend this. So if I click on this link, it'll take you to the workshop page. And Rachada will put up these links online somewhere. So this should be interesting too. It's at Gates 6115, I think. And there are a bunch of different talks, some of which may be interesting. You don't have to attend the entire day, obviously. It's from 8:30 a.m. to 6 p.m. But there are a bunch of talks that may be interesting. So I'm giving a talk on memory system design, for example. Rajiv Balasubramanian is giving a talk on memory security, not the same talk that he would give on April 3rd. It's a different talk. And there are a bunch of companies that are giving talks. Cavium, Hynix. Hynix is one of the 3 major DRAM manufacturers. SanDisk, Ubuntu, and several other Carnegie Mellon professors are speaking. Greg Ganger, Mor Harkolbalter, Eric Xing, and Cisco, I guess, at the end. So there are a bunch of different talks. Feel free to attend these as well. And these are relatively short talks, 20 to 30 minutes. Should be interesting. And these are actually a set of unconventional companies, if you will. They don't normally come to Carnegie Mellon, as far as I know. For example, I don't know if Hynix has ever been to a career fair at Carnegie Mellon. Anybody knows? I don't know. But anyway, there's a career fair, too, if you're looking for internships, for example. And if these companies seem potentially interesting to you, you can go to that career fair during that day. It runs from 11 a.m. to 3 p.m. I guess we have a lecture that day, right? So make sure that you don't go to the career fair during that lecture time. Or maybe we'll do something about the lecture. Let's see. OK? And this is the link to the career fair. OK, hopefully that should be interesting to you. All right, let's start with the lecture material. This is where we left off. This was the last thing I was going to cover in caches, but I told you that this is actually related to not only caches, but any kind of memory. The key question is, how do you make memory higher bandwidth? We talked about non-blocking caches that enable multiple outstanding misses, right? But you don't want to service only misses in parallel, but sometimes you may want to service hits in parallel, right? Cache hits in parallel, or any kind of access in parallel. The key question is, how do you do that? The problem is we can generate multiple cache or memory accesses per cycle in a given cycle. For example, superscalar processors generate multiple accesses per cycle, right? If you have 2 load units, you would be generating 2 accesses per cycle. Vector processors can generate multiple accesses per cycle, right? Because you can be doing a load on a vector, right? And the key question is, how do we ensure the cache or memory can handle multiple accesses in the same clock cycle? You could think of this as consecutive cycles as well, but same clock cycle is harder than consecutive cycles. So we're going to tackle the same clock cycle problem. And this is especially important when you have a superscalar processor. You want to do multiple load accesses in parallel at the same time. There are several solutions people have developed to this problem, and we'll cover some of those solutions. And we'll talk about what different processors have done over time. Banking is the most commonly employed solution today, especially at the higher levels of the hierarchy. In DRAM, for example, we talk about banking, right? In higher level caches, L3 caches. But these other solutions have been employed at the lower level caches that are really close to the processor, because you really need high bandwidth close to the processor, right? Because you could generate multiple loads, and this is the first cache level, and you need to access that memory to satisfy multiple of those loads at the same time. The later levels get filtered accesses because some of them hit in the levels close to the processor, right? So you don't need as much bandwidth at the higher levels in the hierarchy. Higher levels meaning farther away from the processor. In fact, these techniques are applicable to the register file as well. So register files have employed these different techniques too. The highest bandwidth you need is really from the register file, right? Because there, if you're doing if you're executing 8 instructions per cycle, and each of them require 2 operands, you need 16 ports at the same time. You demand 16 values. It's not even loads. Any kind of instruction requires an operand. Well, not all of them, right? OK. Let's take a look at some of these solutions. One solution is true multiporting. Basically, have multiple ports on a cell. And in this case, I guess I show you an SRAM cell over here, the cross-coupled inverter, right? And the idea is each memory cell has multiple read or write ports. If you look at this, this is what it's showing. Remember an earlier picture of SRAM, we had only these 2 transistors, one word line basically, right? That connect the signal and its complement to different bit lines. Well, if you want to have another port, add another word line to the cell and have separate controls that control that word line. Now you can read, you can have 2 reads that are happening simultaneously, right? One read will be enabling this word line and sensing these bit lines, bit 1s and bit 1 bar. And the other read will be enabling this word line and sensing bit 2 and bit 2 bar. Make sense? Simple. Well, of course, there's a cost to it. The upside is now you have truly concurrent access, right? If you have 2 reads that are going to either different cells or the same cell, there's no conflict, right? You can finish those reads, start those reads concurrently and finish those reads concurrently. The problem is it's expensive in terms of many things, right? In terms of latency, power, and area. Why? Well, you've added these new word lines, right? Each port requires another word line, another set of access transistors. And this not only increases the area cost, because obviously, and another set of bit lines as well, because obviously you're adding wires and transistors, but it also increases the latency to access the cell. Can anybody tell why? Yes?
You got to switch all the transistors.
Well, exactly. You got to switch these transistors, and you have additional capacitance over here, right? The capacitance on the cell is much higher, because you've connected a lot more stuff, if you will, a lot more circuitry to this wire over here. And as you keep adding more ports, this is just a 2-ported cell. If you want to have a third port, you add another word line. If you want to add a fourth port, you add another word line. Now your capacitance keeps increasing, and your latency to access the cell, latency to read the data out of the cell increases. Okay? And because your capacitance increases, your power also increases, right? Because power is proportional to the capacitance. You guys know that fundamental power equation, right? No? Some of you maybe. But I'll just write it down, and you can read about it later on. That's not the topic of this lecture. But power to access some circuitry is proportional to capacitance times the voltage square times the frequency at which you do the access. Right? And there's also something else, which is the activity factor. How many things you're keeping active. How many things you're switching in the cell. But in this case, you'll probably be switching the cell. Okay? So it's proportional to the capacitance. That's why this solution actually becomes increasingly expensive as you increase the number of ports. Well, one issue here is, what about read and write to the same location at the same time? What about, read and write to the same location at the same time? So if you have one port reading from a location, another port writing to that location, that's a conflict you really cannot eliminate, regardless of however many ports you add to this, right? You need to somehow impose an ordering to that read or write. And that needs to be handled by the peripheral logic. So you need to have some peripheral logic that determines whether you're reading and writing to the same location or same cell, if you will. And you need to ensure that there's an ordering that's imposed for that. For example, if you're doing that on registers, you need to ensure that the register gets written first and read next, or read first and written next, depending on the ordering of the instructions. Right? And this is kind of an example that I pulled from the internet that shows how you should handle that. Basically, you can have dual port memory cells, and you need to have some semaphore cells. In this case, they call it the semaphore cells. So you have 2 ports. This is the left port. This is the right port. And you need to have semaphore cells that ensure that one port, the 2 ports are not, when one port is reading a location, the other port is not writing to that location, and vice versa. And I assume 2 ports are not writing to the location at the same time, right? That needs to be handled peripherally. Okay, so that's an extra logic that you really need to put in to ensure that this works. Okay, and this is an example of what that semaphore is. Okay, the other, I don't know why this is 1. Let's see. Wow, everything is 1. That should be 2. 2. The other solution to the problem is, instead of adding a real port, why don't we add a virtual port? This idea is virtual multiporting. The basic idea is you still have a single port, but you timeshare it across different accesses. Make sense? You start the second access a little bit later than the first access, and the port is heavily pipelined. By the time you finish the first access, you can start the second access, and you get the data for both accesses in a pipeline manner. Make sense? Or pipelining, in other words. For this to work, obviously, each access needs to be significantly shorter than the clock cycle, right? Because you have a clock cycle in which you want to get the data out, and you're partitioning that clock cycle into multiple accesses. This actually was used in Alpha 21.264, such that you can get 2 accesses, two requests satisfied from the cache in one clock cycle. They clock the cache a little bit higher, well, maybe twice as much as the processor, such that they can do 2 accesses in one clock cycle this way. And they didn't need to add any ports. This is nice, right? Because you don't have a whole lot of area cost in this case. If you can do this, this is great. Is this a scalable solution? What if you want to add more ports? Well, it's tough, right? Then either you need to clock your cache higher, or I don't know what other solution you need to have. Yeah, this is very difficult to scale. If you want to do 8 accesses in a single clock cycle, it's very hard to timeshare a single port if your clock frequency is really high. Right. Okay, hopefully that's simple. The other solution, now I'll have to fix all of these, huh? The third one is having multiple cache copies. So you want to have multiple accesses in parallel, so why don't we copy the entire array of the cache, data array, or multiple memory copies. In this case, if you want to do a load, you have two load ports. Port 1 goes to this copy, port 2 goes to this copy. And loads can proceed in parallel, and you have separate data ports. But stores need to update both copies, otherwise you'll have inconsistency. Right? And this was actually used in Alpha 21.164, the predecessor of the Alpha that used, actually you read Alpha 21.264 processor, right, the paper. Yes?
So for these ones though, do you want each cache to be true dual ported so that like the multiple storing doesn't affect the read-write capabilities on the other end?
So you could do that, yes. You could do that. Or you could share a port, I guess, right?
But that means that when anybody writes to just one cache, let's say you want 5 caches because you're fetching 5 instructions, then all of them become invalidated.
Exactly. Exactly. All of them. Well, when you're writing, that means that when you're writing, you cannot do a read on any copies. That's right. If you do make that design decision, but that's possible, right? So it's a design decision. It's better to have it dual ported such that loads can proceed in parallel with the store. Yeah. But this was used basically before 21.264 until they figured out that this was a better solution for 21.264. So the upside of this is now you can have truly concurrent access on loads, right? But if you have a store, you have a problem. That store needs to go everywhere. So you can do perhaps only one store per cycle if you have only one store port. That's why this is not very scalable also. Because store operations form a bottleneck. Well, there's another reason for scalability. Area is now proportional to ports. Right? And that could be a lot. If you want to add 8 ports, for example, you have 8 times the data store area of a cache. Okay? So the last solution, which is heavily used in many memories, is really banking. It's called banking or interleaving. In this case, you partition the data store into multiple pieces instead of copying it, and separate the addresses based on some bits. Now, we've seen this before. For example, in this case, we have 2 banks. Bank 0 contains even addresses that end with a 0, and bank 1 contains odd addresses that end with a 1. Right? And now you need to route the data, the accesses to the corresponding banks, if you will, because address space is partitioned into separate banks. One key question is which bits to use for bank address, right? Yes?
Probably the lower ones.
So the lower ones hopefully have more entropy, and hopefully it'll give you more randomization.
And also for locality, right? Because you assume the data you're going to be fetching is next to each other, so you want it to be distributed among the caches.
Well, let's assume that you have a cache block. You could still use a higher bit to determine which bank it maps to, and you still have the entire cache block, right? This just determines where that cache block is physically. Okay? Okay. So basically, you would like to distribute the addresses such that you can minimize the bank conflicts. Right? The upside, okay, let's take a look at the upside and downsides here. Upside is no increase in data store area here, right? Data store remains the same here. Whereas data store actually increases in all previous solutions except for virtual multiporting. The downside is if you have access to the same bank, you cannot satisfy them. And we've seen this before in bank conflicts when we talked about vector processors, for example. So you need to distribute the addresses intelligently, or even randomize as much as possible. And some of the solutions that we discussed last time, hashing, for example, could be used here also. You could take some address bits and take that through a randomization function, and that enables, hopefully, more distributed access across the banks. The other downside is the area cost here, right? If you look at this interconnect, now it needs to be much more complicated. And it can be any interconnect, but crossbar is the most flexible one. Because you may have an access coming from this port that goes to that bank, right? Make sense? Because let's say you have multiple load units that are generating loads and stores, and they may generate their addresses such that they go to a bank that's in a different port, that's farther from this port, right? Or any port actually needs to be mapped to any bank. That requires a crossbar interconnect. And output ports similarly require a crossbar interconnect because let's say you access through this port, you do a load that goes to this bank. You expect the data coming out from the port that you initiate the access from the output port. So after this access, the switch needs to be set such that the data goes out of port 0, if you will. Make sense? And you can scale this crossbar as you increase the number of banks. That essentially becomes a crossbar interconnect or point-to-point interconnect. We'll cover interconnects later on. You could actually use many more interconnects, but then now you get contention on the interconnect as well, right? OK? OK. So we talked about bank conflicts. How can these be reduced? Well, you could think about hardware or software methods of doing that. One hardware method we discussed earlier, hashing, for example. Software methods, if the software is aware of the access pattern, it can try to put the addresses that are going to be accessed in an interleaved manner in this bank, right? So the software can try to ensure that the addresses that are not going to be accessed together are put together in the same bank. That may be tough. The software really needs to know exactly what your access patterns are to be able to do that well. But depending on what kind of, for example, in GPUs, part of the problem is that way. Part of the problem is that the programmer needs to deal with these bank conflicts, and programmer needs to try to, if you want to get maximal performance, the programmer needs to map data such that data that's going to be accessed at the same time doesn't map to the same bank, right? Especially if it's going to be accessed by different warps. OK, any questions on this? This is pretty simple, right? OK. So interleaving is actually a general principle that's used across the entire memory system. Let me recap the problem. The problem, if you look at it another way, a single monolithic memory array takes too long to access, and it also doesn't enable multiple access in parallel. We've looked at it from the point of view of it doesn't enable multiple access in parallel. But if you actually design a memory as a monolithic array, it takes too long to access also. So you would like to really bank it for that reason as well, not only to enable multiple access in parallel. If you would like to reduce the latency of memory array access and enable multiple access in parallel, one idea that has worked very well across the entire memory system is to divide the array into multiple banks that can be accessed independently. Independently meaning you can start an access in the same cycle or in consecutive cycles. Right? Each bank is smaller than the entire memory storage, entire memory array, and access to different banks can be overlapped this way. So this idea, banking idea, solves two problems at the same time, because an array takes too long, a large array takes too long to access, break it down into banks, and this also enables multiple access in parallel. A key issue that we've briefly touched upon is how do you map data to different banks? This is also called how do you interleave data across banks? So banking and interleaving are the same. So we'll get back to this in main memory a little bit later on. OK. OK. So there are further readings on caching and MLP. And this is a required reading that I mentioned in the last lecture, MLP array cache replacement. But I'll give you a couple more readings on MLP, memory level parallelism. It's actually a one-page paper that I like a lot. It was in the Wild and Crazy Ideas session in the conference on S+, Architectural Support for Programming Languages and Operating Systems in 1998. And it talks about why MLP is an important thing to consider in designing processors. Andy Glue was one of the original architects of Pentium Pro, one of the 6 architects that did the main design of Pentium Pro, which was the first superscalar processor. Well, first superscalar out-of-order processor, right? That was designed, and that was really successful. Actually, a lot of the Intel's current microarchitectures are based on the Pentium Pro design that was done in early 1990s. But this is a paper he wrote, one-pager, describing a lot of ideas on how you should actually be designing processors that generate many, many accesses in parallel, because that's the main bottleneck. And this is a paper that I had written during my PhD thesis work, which we will cover later on, that talks about run-ahead execution, which is a method of generating multiple accesses in parallel in a cheap way. So these are all related to MLP, memory level parallelism concepts, and this ties in MLP and caching together. And that's the required reading. OK? Any questions so far? So now that we've talked about interleaving, let's jump into main memory, because main memory is very heavily interleaved. I've given you this picture many times before, so you're sick of it so far. But this is what we're going to talk about this time. I think we've talked about a lot of this stuff here. Actually, we're going to talk about not this, but whatever controls it too. Because if you just have memory without a controller, it just doesn't work. Okay, this is the abstraction that I'll use. If you think about the memory system, you can think of it this way. You supplied an address, and you have some data storage that has some number of bits, and that's as denoted here. If the address is n bits, you have 2 to the n locations, and each location can supply you k bits, and you get a data element of k bits. And you can think of the entire memory system like this for one request, at least. You can write enable the memory system, and you can maybe chip enable is not the best way of thinking about it, and you can enable the memory system, right? And as you go lower in the hierarchy, you'll have smaller and smaller structures that resemble this. That's what the memory system looks like. Basically, you can think of this as like snowflakes. When you zoom into a snowflake, it looks like a snowflake, right? Memory system is kind of like that too. Okay, so memory bank, we've seen this before, but this memory bank looks like this also, right? Maybe we don't show the enable signals over here. But memory bank is a 2-dimensional storage array, and any kind of memory has a memory bank that looks like this. And I'm not going to cover this again, but this is just to show you that we'll deal with memory banks. And this is the SRAM, and this is DRAM. They look very similar, and by now you now know why we have separate latches for row address and column address in DRAM, and why we do not have an SRAM, right? Because we don't want to have keep supplying a large address in DRAM, because pins are very costly in DRAM. We want to supply a portion of the address, row address first, latch it, and then using the same address pins, we want to supply the other portion of the address, the column address. This way you can get rid of the pins that are needed if you actually needed to supply the full address in a given cycle. Okay, and we've talked about DRAM versus SRAM. But because DRAM is higher density and lower cost, it has been used as main memory. SRAM is too expensive to be used as main memory. Main memory is farther from the processor. You would like higher density and lower cost as you go farther. There are some fundamental concepts which I'll go through really quickly. Address space, you all know of this. This is a physical address space. Virtual address space is different. Physical address space is the maximum size of main memory. This is the total number of uniquely identifiable locations. Physical addressability is a minimum size of data in memory that can be addressed. Right? Byte addressable, word addressable, 64-bit addressable. This is different from the virtual addressability, which is if you have virtual memory, that's the ISA level addressability, right? Or you can call this the microarchitectural addressability. This depends on the abstraction level of the implementation. For example, you may have memory that operates purely on cache block basis, right? Whenever you access memory, you can only get a cache block and nothing smaller than that. That's possible to design a memory that way. Now that's very different from the ISA. In ISA, whenever you do a load, you can specify whether it does a byte load, word load, double word load, right? Depending on the opcode. Microarchitecturally, you can bring in an entire cache line, and then the load picks the byte later on, right? What is exposed to the program is the byte, but microarchitecturally, the transfer can be done at the granularity of a cache block from main memory to caches. Does that make sense? You can have different addressabilities at different parts of the hierarchy. For example, you can have L1 cache. When you access it, you need to support the levels that are needed by the ISA, right? So its addressability is determined by the ISA. But L2 cache, it's not really exposed because you're not loading the data into a register from L2 cache. Whenever you access the L2 cache, you're loading the data into the L1 cache. In that case, maybe the addressability is at the cache block level, right? Make sense? And as you go down, maybe the addressability increases. Maybe whenever you access memory, you get a page, right? And then later on, you cache that page in an, I don't know, maybe an L5 cache. And then that L5 cache, whenever you access that, you get part of that page and bring it in. OK. Alignment, we've talked about alignment earlier. We're not going to cover that again. Does the hardware support unaligned access transparently to software? So you know the trade-offs here. And interleaving is another fundamental concept that's employed in memory. And we've talked about that. So this gives you a picture of what an interleaved memory looks like. In this case, I show you 2 banks. Assume each bank supplies a word. This is a little bit different from the picture that I showed you earlier. This doesn't require crossbar in the input and output. This requires just a bus. And this is the bus. Basically, you have 2 banks. Assume each bank supplies a word. And this is the memory structure that I showed you earlier, right? Abstraction level. If you look at a bank, it looks like whatever I showed you earlier. You supplied some address, which is not shown here, unfortunately. You supply it write enable, chip enable, and you get out some data, where k is equal to 32 bits here. The bank 1 looks very similar. And basically, in this case, the banks share the address bus. I don't show the control bus here, but they can share the, well, the banks share the data bus, obviously. I don't show the address bus here, but they can share the address bus too. Which means that you cannot get 32 bits out of both banks at the same time, right? In this case, we're gating. Basically, only one of them only one of these gating signals will be enabled in a given cycle, okay? And actually, gate 0 is the same as chip enable 0 probably, right, later on. We just need to synchronize the signals. OK. One key question is which banks are consecutive merged in memory mapped to? Or how do we interleave the words across the banks? And this is what we've briefly discussed. If you have a physical address of 13 bits, and I think I've made the sizes over here such that physical address of 13 bits covers this memory, you could use an interleaving scheme that looks like this. Basically, the bottom 2 bits are the bytes in word, because we're getting 32 bits, or 4 bytes from memory, right? The next bit determines which bank does the 32 bits reside in, right? And the next 10 bits determine which row, because you have 1,000 rows. Okay? This is one interleaving scheme. The other interleaving scheme, this is the bottom bits determine which bank, or the bottommost bit possible determines which bank actually this word resides in, this 32-bit resides in. The second interleaving scheme uses the topmost possible bit. In this case, bit 12 decides which bank this word actually resides in. And the in-between bits are the row bits, right? And this is another interleaving scheme. You can actually pick a middle bit somewhere here, and row address could be kind of chopped in between, right? You could use these 2 things concatenated as the row address. Okay? So you get different kinds of conflicts depending on which bit you use over here. And we've discussed this before. Hopefully, the lower order bits have low entropy, or high entropy, meaning that they change a lot more than higher order bits. So if you do this interleaving scheme, you'll hopefully minimize the bank conflict. But that may not be the case. This really depends on the access pattern, right? What if you have a stride of, in this case, 4 kilobytes, right? If you have a stride of 4 kilobytes, you'll always be hitting, well, I guess you'll always be getting bank conflicts here also. But you'll always be getting bank conflicts here, right? What if you have a pattern that alternates the top bits, but doesn't alternate this bit, right? In that case, this will perform better than this one. OK? So people, for this reason, try to randomize the bits. In fact, many memory controllers today do not use, well, in this case, it's a single bit, but do not use a consecutive set of bits, but they use a hash function to actually randomize the mapping. And we've discussed that before. At the memory controller level, it's easier to do because you have a lot of latency you have a lot of time to do that randomization. At the cache level, access latency is really critical because you need to supply the data quickly to the processor. But the memory controller, you already have lots of latency to access DRAM, so you can actually overlap that latency with the address calculation or hashing. Yes?
So why do we worry about locality in our programs if at the end of the day the data is kind of randomly spread out across the banks? Like, wouldn't they do better if we knew more about how the data is distributed at the bank level?
So it's not randomly spread out. Cache lines could be randomly spread out.
Yeah.
Yeah. So you still, yeah, in this case, this is a toy example, right? So let's say your cache lines are spread out randomly. You still worry about locality within that cache line, right?
Yeah. Oh, I see what you're saying. Okay.
So does that make sense?
Yes.
So it's not this. It's not that your cache line actually takes very long to access because the bytes in the cache line are spread out. Okay, it's the entire cache line is mapped to a single bank, and you get that data. Okay. All right. We'll see that actually. We'll see how it works in the next few slides. Okay. Some questions. Well, concepts actually, more than questions. We've actually seen this before, right? Remember Cray 1 that we discussed earlier? They had 16 banks in that processor to tolerate the 11 cycle bank's latency such that they can get a word every cycle from memory. What they did was they interleaved consecutive words in memory in consecutive banks. Actually, Cray 1 didn't have caches in that case because they had a lot of parallelism. They didn't need to exploit locality. And in their case, one access could be started and finished per cycle. They couldn't start multiple accesses in parallel because memory looked like this, because there was a shared data bus and shared address bus across the banks. Well, can banks be operated fully in parallel? I've already shown you that it can, right? This picture that shows a bank is different from the picture that I showed you earlier, which needed a crossbar in the input and crossbar in the output. In this case, because that required, that enabled, the earlier picture enabled multiple accesses to be started per cycle, right? Whereas this picture, you cannot do multiple accesses per cycle. You can do multiple accesses in a pipeline manner in consecutive cycles, but not in the same cycle. So we've seen this earlier. What's the cost of operating banks in fully in parallel? The cost is that crossbar, right, in the input and output. So people have made the trade-off to use fully parallel banks versus pipeline parallel banks, if you will, at different levels. So modern superscalar processors have L1 data caches with multiple fully independent banks, for example. Whereas DRAM banks share buses, address, data, and command buses. Okay? That makes sense. Well, there's actually another reason for DRAM. It's not only the cost of the ports, but also you don't want to send a lot of addresses at the same time to DRAM, right? Because you're going off the chip boundary. And to be able to supply multiple addresses at the same time, you need to have multiple pins, more pins. Sharing address, data, and command buses across different banks minimize the number of pins. OK. Am I going too fast? Too slow? Just OK? Seems like just OK. OK. So even this bank that I showed you earlier is actually, this is also an abstraction, at least in DRAM. Now we're going to go into DRAM. The 32 bits that I showed you over here, I told you that this bank can supply 32 bits. In modern systems, these 32 bits can actually come from multiple chips, each of which can supply 32 divided by n bits. So even this is an abstraction. I told you that we're going to deconstruct what's that black box that will look like this. And that's the idea of a rank, if you will. So basically, a rank is a set of chips that respond to the same command and the same address at the same time with different pieces of the requested data. So instead of building a chip like this that can supply 32 bits, we can build 4 chips, each of which can supply 8 bits. And they supply different portions of that 32-bit that we want. Why? Because producing this 8-bit per pin chip is much cheaper than producing a 32-bit per pin chip, or 32-pin chip, let's say. Right? It's not per pin. Right? This requires 8 pins out of the chip, 8 data pins at least, whereas actually designing this chip that can truly supply 32 bits requires 32 pins. And your cost is much higher. because DRAM manufacturers would like to minimize their costs, they would rather design a chip like this. And at the system level, you can combine multiple chips, and you can access them as a rank of soldiers, if you will. Right. Basically, the idea is to produce an 8-bit or pin chip, but control or operate them as a rank so that we can get 32 bits in a single read. Make sense? That's the idea of a rank. And the main reason is you would like to minimize the cost of the chip. We'll see this again when we come back to it. But keep this in mind. OK, any questions? All right, let's go into the DRAM subsystem. And I'll show you two views of the DRAM subsystem. This is, you can think of this as the capacity of the entire DRAM. And at the top level, you have a channel. And each channel can contain multiple DIMMs. A DIMM can consist of multiple banks, multiple ranks, as I showed you over here. A rank consists of multiple chips, and a chip consists of multiple banks. And each bank is row and column, right? It's a two-dimensional array of cells which look like rows and columns. So the basic bank structure, let's start from this part. The basic bank structure looks like this. I've shown you this in different ways, but this is an example with realistic values. So a DRAM bank can have 2 to the 24 bytes. In this case, what is 2 to the 24? That's 16 megabytes, right? That's pretty large. I guess it's 16 megabytes, yes. And that could be divided like this, 2 to the 10 columns and 2 to the 14 rows. And you have the row address latch and the column address latch. And you have the row buffer that we've shown earlier, right? And this is an 8-bit or 8 data pin chip. You get the address from the DRAM controller. This is the and that address is supplied to either the row address latch or the column address latch. And you get the command from the DRAM controller. This specifies what to do with the address, or this specifies what to do to DRAM. DRAM today is a pretty dumb device. It just takes addresses and commands. And it just responds with data or does something depending on the command. And some of the commands we've seen, and we'll see a lot more. So this is the data out or in from and to the DRAM controller. So you use the same pins to write and read. And this is the command. A DRAM chip consists of multiple of these banks sharing address, data, and command buses. So you can imagine another bank over here, another bank over here, another bank over here. But what's shared is the address, data, and command buses. So as I've told you before, a DRAM bank is a two-dimensional array of cells organized into rows and columns. A DRAM row is also called a DRAM page, unfortunately. Whenever you look at DRAM literature, it's called a DRAM page too. This has nothing to do with the virtual memory page. It could have, they could be the same. They could be at different sizes. Sense amplifiers, these are also called the row buffer. And you know what this is, right? This is actually a not two-dimensional, but this is a row of SRAM-like cells that basically amplify the data coming out of the row that's accessed. Each address is a pair that looks like row, comma, column. And as we've seen in the first lecture, whenever you want to access a row, a closed row that's not open, that's not already in the row buffer, you need to go through an access sequence that looks like this. Basically, the memory controller needs to send a command called activate. This activate command opens the row. It places that row into the sense amplifiers, and that takes some time. And then the memory controller sends a read or write command, depending on whether you're reading or writing. The read or write command reads or writes the column into the row buffer, right, in the row buffer. And the memory controller later sends a pre-charge command, which actually closes the row effectively and prepares the bank for the next access. Remember, when we talked about DRAM, this sets the bit line to VDD over 2, right, such that the next access to the same bank can be sensed appropriately. Make sense? I'm going through this fast because we already know a lot of this, actually. But the new thing is really these commands. So these are 3 commands that the memory controller uses to open a row, activate, to read or write a column, and pre-charge to prepare the bank for the next access. If you're accessing an open row, which means that the row that you need is already in the row buffer, then you don't need the activate command, but you still need the read and write commands. Yes?
Do you also skip the pre-charge?
Well, depends. Depends on whether or not you want to keep the row open in the row buffer. So what the pre-charge does is it closes the row and enables the array, prepares the array for the next access. If you anticipate accesses to the same row coming later on without any intervening accesses,
You can just keep reading.
you can keep reading. Yeah, you can just keep reading. And existing DRAM controllers actually take advantage of this. This is called page mode DRAM, which should be in a few slides. Yes, actually, this is one of the slides. Basically, you have this row buffer, which is the sense amplifiers. Initially, it's empty. Let's assume that you're accessing address at row 0 and column 0. In this case, it's empty, so the memory controller first needs to activate this row, row 0, which brings the contents of the entire row into the row buffer. And remember, the entire row could be pretty large, right? In the previous picture I showed you, it's 2 to the 10 bits, 1024 bits. Is it 2 to the 10 bits? Let's see. Yeah, actually 2 to the 10 bytes in this case, 2 to the 10 columns, right? So it's 1024, 1 kilobyte basically. OK, once the row is activated, now you can do a read from it. The memory controller sends a read command, which basically, in this case, reading column 0. And the DRAM chip muxes out this column and sends the data back. OK? Later, let's say you have an access to the same row, but to a different column. Assuming the memory controller kept this open, it didn't pre-charge the array after this. Now you can send just a read command to column 1. Basically, send a read command and supply the column address. This is called a row buffer hit, as we've seen before. And it takes much shorter because you don't need to do this activate that was needed previously. And you don't need to do this activate because the row is already open in the row buffer. That's why you get a row hit. And the column address, column data at address 1 is muxed out and sent back to the memory controller. Assume that you're accessing the same row again, column 85. The same thing happens. It's a row buffer hit. And you just need to send the column address and the read command. And the data is muxed out and sent to the memory controller. Make sense? So if your access pattern is nice like this, which means that you have good row buffer locality, it's a good idea to keep the row that you've just accessed open in the row buffer without pre-charging the array. And many memory controllers take advantage of this fact today. This is called the open row policy. Open row means whenever you access a row, and whenever you activate a row, keep it open in the row buffer. Don't pre-charge the array after a read. Why? The anticipation is that you're going to get more hits to the row, more accesses to the row. And if you have really good spatial locality, that's probably a good idea, right? OK? Well, if your next access is to a different row than the one that's currently open in the row buffer, this is called a row buffer conflict. And the memory controller now needs to close this row, which means that it now needs to pre-charge the array, prepare it for another activate, and then send an activate to row address 1, which basically brings the data into the sense amplifiers. And then it needs to send the column address to row 0. It needs to send a read to column address 0. Make sense? OK. So obviously, the latency of a row hit and row conflict is very different, as we've seen in the first lecture. That's why DRAM controllers try to optimize to maximize the use of the row buffer. They try to reorder requests such that things that hit in the row buffer are serviced first. Because if you close the row buffer and reopen it again, then you can incur a lot of latency. Right? And this, remember from the first lecture, this leads to potential denial of service issues, because if a program is always hitting in the row buffer, another program may be denied service from this bank. Another program that doesn't have good row buffer locality may be denied service because the memory controller's policy is hardwired to maximize the row buffer hit rate, or maximally utilize the row buffer that's already open. OK, we'll get back to that also when we talk about memory scheduling. OK, so it's clear now what's activate, read, write, and pre-charge, and what's a row buffer hit and what's a row buffer conflict, right? OK, let's go to the next one. The DRAM chip, I told you that it consists of multiple banks. In today's DRAMs, it's anywhere between 2 to 16. I believe in DDR3, there are 8 banks. Banks share command, address, and data buses. I told you that also. And the chip itself is a narrow interface. In today's chips, you can buy chips that have an interface of 4 bits per read or write, basically 4 data pins, or 16 bits, anywhere between 4 to 16. And this is an example DRAM chip from a data sheet. This is just you don't need to know everything all over here. But this just shows that whatever pictures I was showing to you before are actually real. Yes?
Are we going to get a mystery signal question?
Yes, maybe. not over here. Well, you may get it over here. You should know all of this, right? Basically, what does this show? This shows you, no, not this complicated, obviously. It is actually a pretty complicated chip. DRAM chips are pretty complicated today. But you see here that these are the banks. Let's start with the banks. And you can see how many bits that they provide. I believe it has, so if you look at this is the bank 0 row address latch. You have 8 banks in this chip. And you have 8 row address latches for different banks. And this is the row address mux here. The input of the row address can come from outside, which is the address pins coming into the chip, or something else over here, which is refresh. So the DRAM chip can internally refresh. And we'll talk about that. So when the DRAM chip is refreshing, you cannot access the chip, because obviously you can either select the address that's provided by the refresh counter or select the address that's coming from the input address pins, right? So this gives you a lot of idea of how DRAM chips operate today. But you see that there's this bank control logic that determines which bank the address goes to, and that can come from either here or from the refresh counter also, as you can see here. So in this case, you have 14 bits that is supplied as a row address. So you have 16K rows. And it looks like you have 256 columns over here. Is that right? Well, actually, that's not exactly true. But what's happening here is this is an 8-bit interface. You have 8 data out pins. But internally, what the DRAM chip is doing is, internally, its columns are 32 bits. But the memory controller can read 8 bits at a time. Why? Well, this is a form of prefetching that's employed in the DRAM chip. Whenever you want to read a column of 8 bits, you can only read data at an 8-bit granularity. The DRAM chip internally is fetching 32 bits. You look at the data path over here. It's really 32 bits from the row. And then later, it's latching those 32 bits over here. And based on which column that you really need, it's sending the 8-bit that you really want. Which means that if you want to access the next 8 bits, it's already latched over here, so that access is faster too. So that's a form of prefetching out of the column. This is called the burst mode of DRAM. You don't need to know this, but you can burst out consecutive columns much more quickly than non-consecutive columns, because you prefetch 32 bits and your interface is 8 bits. It's pretty cool, right? So it's very heavily optimized. So if you're reading consecutive 32 bits, that's a great thing. So this is all optimized for cache line reads, such that consecutive reads are done very quickly out of the DRAM chip. OK, what else is here that's interesting? You see the column decoder here, right? Column address latch. And you see that column address latch is fed from a bus that comes from the same address pins. And address pins are over here, bank address and the column or row address. And you have a register that latches it also initially, such that you can operate things over time. You don't need to do everything in a single clock cycle. And this is how you get the 32 bits. Basically, column decoder selects 32 bits out of the sense amplifiers. And that's latched into this read latch. And the 8 bits that you're reading, determined based on the lower bits of the column address. Higher bits of the column address go here. Lower bits of the column address, ignore the circuitry. This is the writing circuitry. How do you write into that latch? It's called a read latch, but you actually write into that too. Well, actually, I'm not sure. Based on this picture, I'm not sure. This is not a very detailed picture, so you cannot tell. Actually, this should be driving over here, but it's not shown here. Basically, you read the 8 bits that you need over here. And that gets this is all for signal integrity out of the DRAM chip. You need to ensure that the signal that you're reading is good, right? But we're not going to talk about that. OK? That's pretty simple. And no, you're not going to get a mystery signal over here. But you may get a mystery signal in this bank abstraction, right? Like which bits are actually used for the bank. Yes?
Why in the bank control logic does it get 2 bits from the refresh counter versus 3 from the address register?
That's interesting. That's a good question. Is that a typo?
There's that not defined in bank control logic. Maybe that's.
Oh, I see. Yeah, maybe, but I'm not sure what that is, actually. I don't know. I haven't thought about it carefully. You have a good eye. Because you should really, or maybe what's happening, what might be happening is so what happens in DRAM is you can actually refresh multiple banks at the same time. So maybe that's what's happening. Maybe that's a don't care, and you're refreshing all the banks that have these 2 bits set. That's my guess. If this is true, that would be my guess. The other option is this may be wrong. Or maybe, I don't know what this dotted line is actually at all. But the first option makes sense. OK. Let's go to the next thing, if this allows me to. OK. So DRAM rank and module, I've already told you that multiple chips are operated together to form a wide interface, and that's called a rank. All chips comprising a rank are controlled at the same time. They respond to a single command. And they share address and command buses but provide different data. Well, this is exactly why it's called a rank. Right? It's a rank of soldiers that respond to a single command. Right? They provide different data because everybody's actions are different. A DRAM module consists of 1 or more ranks. This is also called, for example, a dual inline memory module. And this is what you plug into your motherboard. Right? You can have 1 or more ranks. Basically, if you have chips with 8-bit interface to read 8 bytes in a single access, you can use 8 chips in a DIMM, right? And that's what a lot of processors use today. They have a 64-bit bus, and in order to read those 64 bits in a single access, you can have 64 bits, 8 bytes, right? You can have 8 chips with an 8-bit interface. And if you look at a DIMM, which is here, 1, 2, 3, 4, 5, 6, 7, 8. You've seen this before, something like this before, right? Yeah, that's why you have 8 chips over here. And each of them provide 8 bits. They go to different data, but they do share the command buses. And, well, there should be an address bus here, which is not shown, and the address bus too. OK? So this is another view of the DIMM, if you will. You have 8 chips over here. Each chip looks like this. It has 8 banks in this case. And each chip supplies 8 bits. And they're aggregated to a 64-bit wide channel. And that is connected to the DRAM data bus. And they share the address and command buses. The chips share the address and command buses. Okay? The advantage of having a rank, making the interface wider, this acts like a high-capacity DRAM chip with a wide interface, right? This way, you don't need to build chips that can provide 64 bits at one shot. This becomes cheaper. The DRAM part becomes cheaper, right? And you also get capacity, right, this way. It also provides flexibility. The memory controller does not need to deal with individual chips within a DIMM, right? It needs to deal with individual banks, but not with individual chips. The disadvantage of this wide channel, or wider channel, is the granularity. Right? Accesses cannot be smaller than the interface width. You cannot, for example, access a single bit. You need to access 64 bits. Or you cannot access 8 bits. You need to access 64 bits. And then you need to pull your data out of that. OK? So you can have multiple DIMMs. If you want to get more capacity, now you can have multiple DIMMs on a single rank or on multiple ranks. This is a terrible picture that shows that example. But you can imagine some topology. You don't need to deal with following these arrows. But basically, this shows that you can have multiple DIMMs connected in some way. You could have a daisy chain of DIMMs also, right? Which is probably a bad choice in terms of the design. For example, the there was something called fully buffered DIMM that was very popular because Intel decided to implement it in its memory controllers in around the 2000 era, I think. And its interface was a daisy chain. You had one DIMM over here, and then another DIMM, another DIMM, another DIMM. You didn't have a topology interconnect that looked like a mesh or that looked like a mess like this here, but it was a daisy chain. Basically, you would have a little controller here that checked if the address belonged to this DIMM. If not, it passed the address and the command to the next DIMM. And you would have a controller that would check, again, if the address belonged to here. If not, it passed it to the next DIMM, and then dot, dot, dot. It's a terrible interface because your latency could be really large, right? You're individually trying each DIMM to figure out whether the address belongs there. But OK, this is what it takes to actually get higher capacity. And if you want to get higher capacity, you keep adding more DIMMs. The downside of this is now your interconnect complexity and energy consumption can become quite high, right? Because you need to add good interconnects to keep latencies in check. If you want to do a daisy chain, which is the simplest interconnect, your latencies could be very high. Because to access DIMM 16 over here, you need to go through DIMMs 0 through 15, right? Or DIMM 15 over there, you need to go through DIMMs 0 through 14. OK? So this is one of the reasons why DRAM capacity cannot get higher and higher by adding more and more DIMMs, because it becomes more complex. And DIMMs are the main way. There are many ways to improve capacity, actually. You can improve the density of these chips, which we will talk about later. You can add more rows in each chip. Now in each bank. Now your banks become larger. Or you can add more DIMMs, right? And they all have different trade-offs. You can think of those different trade-offs. If you want to add more DIMMs, now your channel complexity becomes higher. OK? And also the loading on the channel becomes higher as well. OK. So DRAM channels, well, I've talked about channels. But DRAM channel is essentially what the DRAM controller controls. In this case, if you look to the left, I've copied the picture that I showed you earlier. This DRAM controller controls this channel. And it's a 64-bit wide channel. And you can add another channel by adding another DRAM controller to another set of DIMMs. Now, in this case, I show you two DRAM channels, right? And these are controlling two different channels, completely separate channels. It's called two independent channels also. If you want to build an even wider interface, such that you can get 128 bits, consecutive bits, at one shot, you can have a single memory controller controlling both channels in a manner such that both channels respond to the same command and provide consecutive pieces of the consecutive 64 bits of data, right? That's called dependent or lockstep channels. Basically, one memory controller with a wider interface. In this case, these 64 bits can be completely independent because you have two different controllers. But if you have a single controller controlling a 64-bit channel here, a 64-bit channel here, you can get 128 bits that are consecutive in memory, while 64 bits pieces can be consecutive in memory. And now you can have a wider interface. And people have implemented both kinds of channels. The channels that you have in today's processors are usually independent channels, such that you can supply more data, more independent pieces of data to multiple cores. OK? All right. So I think I've kind of built bottom up the memory structure. We've started with rows and columns. And if you memory or DRAM usually is thought of a 5-dimensional structure as a 5-dimensional structure. And we will probably figure out the dimensions soon. But you have a 2-dimensional array of cells, columns and rows. And a cache line is mapped to something like this in a bank. And you have a bank, a chip, a DRAM chip consists of multiple banks. And a rank consists of multiple chips. And you can have one or more ranks in a DIMM. In this case, I don't show the DIMM. And a channel can consist of one or more DIMMs. And you can have more channels. Make sense? And the memory controller is responsible for controlling a channel or multiple channels that are dependent. And that's another way of looking at it. This probably shows a 5-dimensional structure better. OK, any questions? So in the next few lectures, we're going to cover a lot about DRAM. But let's actually take a break for 5 minutes, and then we'll see the top-down view, and we'll go into some of the issues in DRAM in more detail. OK, let's be back according to that line out of the DRAM subsystem. This is what I showed you earlier. Let's start with the channel. So if you look at your motherboard today, you will see something like this. Not exactly, but you will see something like this, right? The processor is connected to a channel, and a channel can have multiple DIMMs. In this case, this is a DIMM. Okay, let's go into a single channel. Well, basically, you have one of these DIMMs. And if you look at a DIMM, it looks kind of like this, right? It has two sides, and you can have chips on the front and chips on the back, right? That's basically the two ranks. And rank is a collection of 8 chips. You have rank 0 and rank 1 in this case. So how do these ranks get connected internally? Basically, these ranks look like this. They actually share the address and command bus, but they have different chip selects. So they can be accessed independently. But there's actually a rank switching penalty because they actually share the address and command and data buses, right? Basically, there's a mux that muxes out the address and data from from different ranks. And this is basically your memory channel. Well, if you have multiple DIMMs, then you have another mux over there. It depends on your interconnect topology. If you break down a rank, internally it looks like this. Basically, it consists of multiple chips. I showed you 8, which supply, in this case, 8 bits each, and 8 consecutive bits of a total of 64 bits, 64-bit data bus. And then if you break down each chip looks like this. Basically, you have 8 banks, and they all supply 8 different bits, and they share the address, command, and data buses. And there's a mux that picks the data that you're going to read. OK? And if you break down a bank, basically it's the two-dimensional array of cells that I've shown you earlier. And you've seen this before, right? Basically columns and rows, and you have the row buffer, and you mux out the column that you need. OK? It's kind of cool. And I'm not going to break this abstraction level right now, but this actually internally consists of even smaller structures called subarrays, because it turns out the latency to access, in this case, 16,000 rows. Basically, if you want to access 16,000 rows as a single monolithic structure, the bit lines that you have will be very long. And the capacitance of that bit line will be very high, and your latency to activate a row would be really high, actually. So internally, what happens is this is broken down into smaller substructures called subarrays, of which there could be 128, let's say. And each subarray is much smaller. It could have 1K rows, for example, or 512K rows. Not 512K rows, 512 rows. If you have 512 rows, and if you have 16K total rows in a bank, basically you have 32 subarrays, right? Yes. And internally, basically, you access that subarray, and then that subarray's data is amplified in its own row buffer and then driven out of the chip. And the reason is it takes too long to drive a very long bit line that goes over all of these 16K rows. So why not drive a smaller bit line and amplify the data, and then drive that amplified data out of the chip? And you could do this at the subarray level by dividing this into multiple different smaller pieces. But that's not exposed to the memory controller today. But we may later cover some ideas that expose this to the memory controller. OK. And you could internally divide the subarrays into smaller pieces, right? That goes back to what I showed you earlier. Again, if latency is a problem, you'd like to divide a memory array into subarrays. And bank is one kind of subarray that's exposed to the memory controller. But internally, it's divided into subarrays to minimize the latencies as much as possible, too. OK. So how do you actually transfer a cache block out of this DRAM chip? Let's take a look at that. Assume that this is your physical memory space. Assume that we're reading the cache block that's starting from address 0. And assume that it's mapped to rank 0 and DIMM 0 in channel 0, based on some address bits. In order to transfer this cache block, the memory controller basically needs to issue commands. It needs to activate row 0, and that means that that activate command is sent to all of the chips in that particular bank in that particular rank, right? In this case, these chips need to be activated. And then you need to send a read command to column 0, which basically brings the first 8 bytes, right? Because we have a 64-bit interface. And then you need to send a read command to the next column, which brings the next 8 bytes. And then you need to send a read command to the next column, which brings the next 8 bytes. So if you want to read 64 bytes, you need to send 8 column commands, 8 column read commands. And it takes 8 I/O cycles or 8 data bus cycles to transfer. So 8 columns are read sequentially during the process. Make sense? OK. So there are a bunch of latency components to enable that cache line access, cache block access. And this tells you where the latency is gone. First of all, the CPU or the core needs to send to the controller, I want this address. Later, that address can wait in the controller. There could be queuing and scheduling delays at the controller because there may be other requests that are being serviced. And the controller converts the access request to basic commands. And commands are activate, read, write, precharge. And then there's transfer time of the command from the controller to the DRAM, right? And the data as well, if you're doing a write store. And then there's the DRAM bank latency. This could be variable. Well, this could be variable too, right? The controller latency, because it depends on the queuing delays. But this could be variable depending on the status of the row buffer. It could require just simple CAS, column address strobe. This is also read or write, right? If the row is open. Basically, you just need to send the column address, or RAS, row address strobe. This is another terminology that you should be familiar with, because some DRAM manufacturers actually use the CAS and RAS commands. If the array is precharged, then you need to send the row address strobe. Basically, you just send an activate and a column command. And in the worst case, if it's a row conflict, then you need to send a precharge, and then activate, and then read or write. Now, after that, the data gets into the controller. And then there's transfer time from the DRAM. Well, before that, I guess, there's transfer time at the I/O bus. This is the bank access latency, and this is the data bus access latency. There's time to transfer the data from the DRAM to the controller as well, right? And that's the bus latency. That's also specified in DRAM data sheets. So this is all specified in the DRAM data sheets. DRAM data sheets actually contain hundreds of timing parameters that you really need to know if you're implementing a memory controller. And later, once the data gets into the memory controller, the controller transfers that back to the CPU, and there's that time as well. OK, so let's take a look at some of the concepts that we've discussed. We talked about multiple banks, and we talked about how they enable concurrent DRAM accesses. Multiple independent channels serve the same purpose, actually. But they're even better because they have separate data buses, right? This enables increased bus bandwidth. If you want to enable more concurrency across both banks and channels, this requires reducing the bank conflicts and channel conflicts. And they're very similar, depending on which address bits you use for the channel, you get different kinds of channel conflicts. And a key question across the entire memory system is how to select or randomize bank and channel indices in the address. And we've talked about this. Lower order bits have more entropy, and randomizing hash functions can enable better distribution of addresses, accesses to banks and channels. Well, I guess this is one example of how multiple banks and channels actually help. And this is pretty simple. So if you have a single bank, this is what you would get. You send the address, you wait for DRAM access, and you can send the next address only after the DRAM responds, right? So you cannot overlap accesses, whereas if you have a shared data bus, and a shared address bus, after sending the address that goes to bank 0, immediately you can send the address and command that goes to bank 1. And then after that, immediately you can send the address and the command that goes to bank 2, and then so on. This way, you overlap the latencies of different bank accesses, and the data comes in consecutive cycles, consecutive data bus cycles. And if you would like to maximize your utilization of the data bus, which is a good goal to have if your data bus is the bottleneck, then ideally you shouldn't have any bubbles in your data bus, right? If you have enough requests coming into your memory. Okay, so multiple channels are similar to this. They enable independent increased bandwidth, and they enable multiple concurrent accesses, assuming they're independent. The disadvantage is that now you have higher cost than a single channel, right? Because you need more pins out of the memory controller, and especially if your memory controller is on the processor die, processor chip, your processor chip becomes more costly, right? If you have multiple channels. If your memory controller is not on the processor chip, which is not the case in today's processors. In today's processors, memory controllers are actually on the same chip as your processors. But if in the old days, memory controller was off chip, and we'll see the trade-offs in the next slide. But if your memory controller is off chip, your memory controller chip becomes more costly if you have multiple channels, right? And you have more board wires, obviously, if you have multiple channels. So this is one example of address mapping in a single channel. And this is assuming a single channel system with 8-byte memory bus, 2 GB memory, 8 banks, 16K rows, and 2K columns per bank. Which bits you use as the bank bits determine how you interleave data across the different banks, right? And there are two common methods today that are used. One is called row interleaving, and the other is called cache block interleaving. This is more fine-grained. This is more coarse-grained. Row interleaving says consecutive rows of memory are placed in consecutive banks. Right? It's pretty simple. If your row size is, if your row size is 2 kilobytes like this, because column requires 11 bits, consecutive 2 kilobytes are in consecutive banks in this case. Right? Which means that accesses to consecutive cache blocks are residing in the same bank in this case, right? Because usually a cache block is much smaller than the size of the row. In this case, the size of the row is 2 kilobytes. A cache block is 64 bytes, which means that you have, how many cache blocks do you have in that row then? 2 to the 11 divided by 2 to the 6 to the 5, right? 32 cache blocks you have in a row. So consecutive cache blocks can be serviced in a pipeline manner because they go to the same bank. And they're all row hits, right? Basically, you open the row, and you keep sending read commands to read consecutive cache blocks. If you do cache block interleaving, the idea is to have consecutive cache block addresses in consecutive banks. And this is what it shows, basically. If this is these are the bits that you use for your cache block plus the byte and bus. And you pick your bank bits from the lower order. It's more fine-grained. With 64-byte cache blocks, this is what you get. In this case, accesses to consecutive cache block can be serviced in parallel from different banks. OK? And there are different trade-offs. Depending on your access pattern, one could be better. So if you have really good row locality, if you will, if you expect really good locality within a chunk of 2 kilobyte memory, this may be a good idea, right? If you don't expect a whole lot of locality, maybe this is a better idea, right? OK. This is one example of bank mapping randomization some DRAM controllers used. Basically, DRAM controller can randomize the address mapping to banks so that bank conflicts are less likely. And one very simple randomization function looks like this. Basically, you use some bits from here in addition to the original bank bits that I showed you over here to form the bank index. Actually, it could be any bits over here as long as you have a one-to-one mapping, right? OK. So this address mapping actually gets much more complicated. Yes?
I guess I was a little confused by what you said earlier, that if you have accesses from multiple banks, you could do them in parallel. But aren't those banks multiplexed?
Yes. So you could do them in you could enable multiple banks in parallel, but yes, eventually they're multiplexed into one data bus. Okay. Yes. Okay. So actually, if you're reading consecutive cache blocks, it doesn't matter whether you do cache block interleaving or row interleaving, because you pipeline out of a single bank over here, or you actually pipeline across different banks here. But which rows are open or what data elements are in the rows is affected by this mapping. And other access patterns may see different behavior. OK? That's a good point. You can do them in parallel in the banks, but not across the interconnect. Or that's also called the peripheral logic, address, command, and data buses. You cannot share them across banks. well, you cannot do accesses in parallel at the peripheral logic. Okay. So this address mapping actually becomes much more complicated, and this is one example. Is this multiple channels? Yes, with multiple channels, you need to also pick the channel bit, right? And also, there's a rank bit I did not even talk about over here. There needs to be some bits that are needed for rank. So do you pick it here? 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 Or do you pick it somewhere in between? And in all cases, where are consecutive cache blocks? I'm not going to ask you this question, but I'll let you think about it. Basically, there are many possibilities as to how you pick these bits. And this is a difficult problem to solve to get the best performance. It's not clear what's the best way of picking these bits, or what's the best way of randomizing these bits. Okay. Basically, this slide is to show you that it's complicated to do this address mapping, and there's no single best way. You really need to look at your access pattern, or find a mapping that works best on average. And randomization in general is a good technique because it gets rid of these cases, or it curbs these cases where your performance can really go bad because of bank conflicts. Because randomization enables, hopefully, minimization of bank conflicts if you have a good hash function, which may not be this. XOR is a easy to implement hash function, but it's not necessarily the best randomizing hash function. Okay, so I've shown you this before, actually. This is the interaction with virtual to physical mapping. Operating system actually influences where an address maps to in DRAM. Why? Because operating system can have a say in which bank and which row, and potentially which column a virtual page actually resides in, because these bits that are assigned to the bank, row, and column change during the translation from virtual address to physical address. And if the operating system knows the mapping of a physical frame number to the DRAM address, then it can do intelligent decisions potentially, right? It can say, oh, I'm going to map this virtual page to this bank. It can do page coloring, basically, as we've seen before. It can assign different colors to different banks. And when it's assigning a physical frame to a virtual page, it can say, oh, I'm going to pick bank 0 for this, for some reason, right? Maybe it wants to separate different processes to different banks, such that each process can get its own bank and can access, it doesn't interfere with other processes in that bank. Right? That could be one reason. Or it may want to separate different processes to different channels, such that they can access the different channels independently. Yeah, basically it can perform page coloring to minimize bank conflicts or minimize inter-application interference. And one of the papers I recommended earlier tries to do that. The problem today is this mapping of this DRAM address is not exposed to the operating system. So it's in that sense, the operating system doesn't have enough information to do this mapping intelligently. Even though it has some control through this virtual memory translation mechanisms, it has no idea where row is mapped to, where physical frame is mapped to in the DRAM topology, because that's not exposed in modern systems, at least general purpose systems. So going forward, hopefully that will be exposed such that the operating systems or the hypervisors become more intelligent in their page mapping decisions, such that you get better performance. But you can imagine why it's not exposed, because the hardware manufacturers try to control that mapping, right? If you look at this, they want to get better bank conflict randomization, for example. And every time you change the hardware, if you change these bits, then you need to change the operating system also if you want to get good performance. Okay, this is a performance optimization, so it doesn't affect correctness. That's the good part. If the operating system wants to minimize bank conflicts to do page coloring, it doesn't affect correctness, right? Okay, any questions? All right, let's move on to memory controllers. Basically, we were actually talking about memory controllers before, but I want to go into a little bit more detail, and we'll talk about memory scheduling later on. Let me pull back a little bit. We've been talking about DRAM, but many other types of memories that are long latency have similar characteristics that need to be controlled. What I'll talk about in the next few lectures, we'll use DRAM as an example, since that's the most commonly employed main memory technology. But many scheduling and control issues are similar in the design of controllers for other types of memories. What are these other types of memories? Well, flash memory. Flash memory actually has very complicated controllers that do the control. We're not going to talk about that. It's part of the storage system today, but it still has controllers. Other emerging memory technologies, we'll dedicate a lecture to this. There are other technologies that have some potential benefits over DRAM. Phase change memory, for example, is a non-volatile technology whose access time is within the order of DRAM. Flash memory is very slow. If you want to read from flash memory, it takes much longer than DRAM, whereas phase change memory is in the same order of magnitude of DRAM. Spin transfer torque magnetic memory is actually much similar to DRAM. Its access time is very similar to DRAM. Now, these have other issues that need to be solved to be enabled, but the controllers that you design for them and for flash memory can use similar scheduling and control algorithms. But these other technologies can place other demands on the memory controller, which we will talk about when we talk about heterogeneous memory systems or these emerging technologies. For example, flash memory, whenever you write to a cell, it wears out. Right? And a cell dies. You cannot write to a cell anymore. You cannot read the data correctly from that cell if you have done, let's say, 3,000 writes to that particular cell. So the controller's job is to ensure that a cell is not written to more than 3,000 times. Okay? So all technologies have their esoteric characteristics, if you will. DRAM needs to be refreshed, for example. That's a problem with DRAM. As we will talk about these memories, you'll see that there's no universal memory technology, unfortunately. It's not SRAM, it's not DRAM. What I mean by universal memory technology, it's universally good in all of the metrics that we want. It's not SRAM, it's not DRAM, it's not flash memory, it's not phase change memory, it's not spin transfer torque memory, it's not magnetic memory, hard disks. They all have their trade-offs. And controllers need to control those characteristics. In DRAM, it's refreshed. In flash memory, it's wear out. In phase change memory, it's also wear out, actually. There are other issues over here, too. But we'll hopefully get to talk about that. So phase change memory wears out, too. How many of you knew that flash memory actually wears out? Oh, OK, a lot. But it's a bit sad to think that if you keep writing to all of these USB devices, they'll be dead at some point, right? Or flash USB device, at least. OK, what are the functions of a DRAM controller? This is actually, well, I'll focus on DRAM, but keep in mind that a lot of these functions are shared across many different technologies. Well, the first most important function of any controller is to ensure data integrity, ensure correct operation. Well, in case of DRAM, the correct operation comes from two things. You need to keep the data the integrity. You need to refresh the data. And you need to ensure the timing is obeyed, because there are timing constraints in DRAM that need to be obeyed such that you can get the correct data. And we'll see some of those. And this is true for other technologies as well. Other technologies may not require refresh, but they have timing constraints. Whenever there's a deterministic amount of time that you need to wait before sending a particular command after a particular command, because the array needs to be ready, right? And they need to control wear out, for example, in some other technologies. The second big function is it should service DRAM requests while obeying timing constraints of the DRAM chips, right? There are many constraints, resource conflicts. For example, you cannot, when a bank is being activated, you cannot send another activate to that bank. You'll have undefined operation in that case. If when the bus is transferring data, you cannot. You need to schedule accesses such that two pieces of data don't come at the same time, right? And there are also channel conflicts, and there are minimum write-to-read delays as well. For example, after writing to a DRAM chip, you cannot do a read after n cycles, let's say, and this n is dependent on the DRAM manufacturer. Why? Because there's a bus turnaround time. When you write, you turn the bus in one way, you supply the data, you drive the bus in this way, and when you are trying to read, you need to change that direction, right? And that takes some time, such that the circuit is stable. So all of these need to be managed by the controller. And of course, while doing this, it needs to translate requests to DRAM command sequences. And we've seen this before, right? You get a request to a row and column address, and you need to translate it to activate, pre-charge, read or write. The third function is the DRAM controller needs to buffer and schedule requests to improve performance. And this is important. A lot of the optimizations that we will see will try to schedule requests in different ways to improve performance. To enable this, the controller does row buffer, bank, rank, and bus management, and also aggressive request reordering. And we've seen one of that request reordering mechanisms before, right? If there are requests to the row that's already open, prioritize those requests over others. And there's also other things, managing power consumption in DRAM, because power consumption is really important. And actually, memory consumes a lot of this overall system power in today's systems, especially in mobile systems. Managing that power consumptions and less so the thermal profile of DRAM is important. And this is done by the DRAM controller again, by turning on and off DRAM chips, managing different power modes. We'll very briefly talk about that. One key question in the DRAM controller is, where do you actually place the DRAM controller? I've alluded to this earlier. One possibility is to place it on the CPU chip where the cores are. Another possibility in the chipset, basically not on the same die as the cores. And this used to be what processor manufacturers did earlier. Intel, for example, they didn't only manufacture processor chips, but they also manufactured memory controller chips or chipsets, right? Or other manufacturers could manufacture chipsets or memory controllers. This enables more flexibility to plug different DRAM types into the system. It doesn't tie the DRAM type or main memory type to the core processor chip. That's the upside. That's the big upside. And this also enables less power density in the CPU chip, because CPU doesn't have a memory controller going on at the same time. On the CPU chip, if you actually put the memory controller on the same die as the CPU, as the processor, you get reduced latency for main memory access, which is good because you don't need to go through another chip, another board wire to access memory. And you get higher bandwidth between the cores and the controller. That's the main advantage. For example, when AMD first put the memory controller on the same chip as the processor, they saw a latency reduction to memory, main memory. I believe their latency reduction was about 30%. And I think that motivated Intel to finally put their memory controller on the same chip as the CPU, which had always been a good idea. They should have just done it earlier. And this also, this more higher bandwidth, because on chip you have a lot of bandwidth, right? Once you go off chip, you need to go through that narrow interface. And the interface is narrow because it's expensive to have more pins. Once you have higher bandwidth between the cores and the controller, now you can communicate more information between the cores and the controller. Now you can do much more interesting scheduling policies. For example, a request importance in the processing core. Where is it in the reorder buffer can be communicated to the controller, right? Such that the controller can prioritize a request that's more important to the processor. Whether a request is a prefetch, whether it's caused by a load or a store, it's needed by only loads or stores. All of this information can be communicated such that the scheduler can be more intelligent in prioritizing the requests. For example, if the memory controller is in the chipset, if you want to communicate whether a request is a prefetch or not, you need an extra pin. Or you need to reuse one of the pins and reinterpret them somehow, which hasn't happened because all of the pins are in use. So that extra pin is costly. And and sometimes you want to prioritize prefetches differently from demand requests because your prefetches may not be accurate, right? Because of this, when the memory controller was on the chipset, the memory controllers didn't really care whether the request was a prefetch or a demand because they didn't know. So they applied a uniform scheduling policy, which is not as good as the ideal scheduling policy because prioritizing demands over prefetches is a good idea sometimes. Whereas if you put the memory controller on chip, now you can say, oh, this is a prefetch request, so treat this prefetch at a low priority than the demand request. And that's easy to do because you just add another wire on chip. That's not costly. That doesn't add more pins. Well, that's costly, but that's not as costly as adding one more pin, right? OK. By the way, it turns out that you don't always want to prioritize demand requests over prefetch requests. Sometimes you want to prioritize or keep the priority of the demands and the prefetches the same. Can anybody guess why? Yes?
Maybe instruction prefetching? Like data?
Actually, that's a good point. I wasn't thinking of that, but yeah, maybe you have you're prefetching for instructions, and you're very accurate, and you may want to prioritize that over a data demand request, because if you don't get that instruction early enough, you'll stall the entire pipeline. Right? That could be one reason. Even for data prefetches, if some of the prefetches are really accurate, you would like to keep them as same priority as demands, because if you deprioritize a prefetch, you may not exploit the robo for locality really well. Right? You may have demands that are destroying robo for locality because they're prioritized, whereas prefetches may have really good robo for locality. You could be accessing the roboffer and getting done with those prefetch requests quickly if you actually kept them as at the same priority as demands. Does that make sense? OK. So it's interesting to figure out what the best policies are between prefetches and demands, and between different types of requests. So let me show you pictures of the DRAM control, and then I'll conclude. Basically, a modern DRAM control is actually pretty complicated because it needs to perform many functions. And this is one example. And it also actually gets requests from different kinds of streams. It's not only the CPUs. It could be the I/O, the DMA engines, for example. It could also get requests from other kinds of cores, like GPUs or accelerators. In a system like this, for example, the memory controller gets requests from many, many different things. So this is incomplete for a system like that. Basically, it needs to perform arbitration. It needs to do bank management. It needs to queue requests. And it also needs to finally, when it sends a request, there is a signaling interface that needs to be implemented over here, which is mainly analog. But this is a simplified view of it for an on-chip memory controller that gets requests from different kinds of L2 caches, if you will. Let's assume that you have many L2 caches, 0 through N1, N-1. These caches send their requests to different request buffers. This is one way of designing the memory controller. You can have different request buffers for different banks. In this case, we have B banks. And you can have different schedulers for different banks. This is the hierarchical organization of the memory controller. Each bank selects a request or command to be scheduled onto DRAM. And we call this the bank schedulers. And then there's another arbiter. So there's an arbiter that selects which command needs to be sent from this request buffer and from any of the B request buffers. And then there's another arbiter, a global arbiter, that arbitrates between these bank schedulers and decides which command needs to be sent to DRAM. This is a hierarchical organization. There are other ways of doing this. You could actually have a monolithic request buffer. And again, this goes back to static versus dynamic partitioning of the space across different schedulers. This is very similar to you have distributed reservation stations versus monolithic reservation stations, right? So the trade-offs are relatively similar. OK, let me cover these policies, and then we'll be done, hopefully. So this is not a scheduling policy, actually. It is a scheduling policy, but there is no reordering that happens. This is the simplest one you can think of, right? First come, first served. Oldest request first. That has been employed, actually, in the past. The old Pentium 4 controllers had first come, first served request scheduling, and that was not good. Because that didn't even exploit robo for locality very well, right? The most commonly used implemented scheduling policy is a variant of this today. It's called first ready, first come, first served. Basically, it prioritizes row hit requests in the buffers over here. And all else being equal, it prioritizes older requests. So row hit requests are prioritized because they take much shorter to service. The goal is to maximize row buffer hit rate and maximize DRAM throughput. And we've seen that this is actually not good in terms of starvation, right? And we'll talk about that a lot more when we talk about DRAM scheduling, memory scheduling. So actually, scheduling is done at the command level. As you've seen, column commands are prioritized over row commands, right? Column commands are read and write, and row commands are activate and precharge, and column commands are prioritized. It's the same thing as saying this. And within each group, column commands or row commands, older commands are prioritized over younger ones. That's how you implement this policy at the command level. let me talk a little bit about scheduling policies. A scheduling policy is essentially a prioritization order, right? The DRAM controller actually determines a prioritization order across the requests that it sees in its request buffers. It could be based on many things. It could be based on the age of the request, row buffer hit miss status, request type, prefetch, read, write, GPU requests, I/O requests, video encoder requests, right? It could be anything. Requester type, load miss or store miss. Well, I guess this could be requester type. You could consider a GPU request as a requestor type also. Request criticality, is this the oldest miss in the core? How many instructions in the core are dependent on it? So you can exercise your imagination and you can come up with different things. Some of these are implemented in existing processors, some of those are not. For example, request criticality is not communicated today to the memory controller, which could be an important thing, right? Let's see. How much time do we have? I guess we don't have a whole lot of time. So maybe I'll leave you with that. You can think of some DRAM scheduling policies, and we'll start with row buffer management policies and continue into DRAM scheduling in the next lecture. Okay?